This is an example of solving Laplace's equation in a spherical region subject to a prescribed function on the surface that's symmetric with respect to rotation around the z-axis. So here's my sphere, as usual. This is the azimuthal angle theta. We're saying nothing depends on theta in this problem, so there's no theta dependence. And the angle that we do care about is phi, the polar angle. So we have some point up here on the surface, the angle, and the polar angle is phi. And so now I want to specify the value of the function on the surface, and let's suppose that the top, the northern hemisphere is hot. So f theta is going to be equal to 110, oh that's really hot, 110 Celsius on the northern hemisphere, so that's phi going from 0 to pi over 2, and then let's say it's 0 on the southern hemisphere, so pi over 2 phi to pi. Okay, and so like we discussed in class, the general solution to Laplace's equation in a spherical domain we can write as un of rho and phi is equal to rho to the power of n and Pn, which is the nth Legendre polynomial of cos phi. Okay, so we can, of course, as usual, use an arbitrary superposition of these guys, and in general our function u will be sum from n equals 0 to infinity of c, sorry, let me call the coefficients in the expansion a sub n, rho to the n, p sub n of cos phi. Now we have to have that at the surface u evaluated at rho equals capital R. Capital R is the radius of my sphere. That has to be my given surface function. But so I can just put in, so this is a sub n, R to the n, p sub n of cos theta. So this is a Fourier-Legendre series for f of phi, where the coefficients in the Fourier-Legendre series are this a sub n, which I can choose, times r sub n, which is just sitting there as a factor that I don't have control over. Okay, and so as usual, how do we find coefficients in a Sturm-Liouville expansion? We have to project. And so remember, for the Legendre, the p function was 1 minus cos phi squared. The q function was 0. The w function was 1. Okay, so since the w function is 1, projection just means integrating with respect to the cos phi variable. So projection, so the projection formula, a sub n, is going to equal, and I have to integrate from 0 to pi. The thing that I'm integrating is f of phi. Sorry, this is actually a sub n Rn, because my coefficient in the expansion is a sub n times an extra factor of r to the n. A unit sphere, if we were taking a unit sphere, this factor of r to the n would go away, but let's keep it there for dimensional purposes. So I have f of phi, and then my eigenfunction from the Sturm-Liouville problem is just Pn of cos phi, and then I have to integrate w times d, and remember the variable, when we wrote the our angular equation in Sturm-Liouville form, we needed to make a change of variables, and cos phi is actually our variable, so I have to integrate with respect to cos phi. Okay, so my function f of phi is equal to 110 in the northern hemisphere and 0 on the southern hemisphere, so I can really just integrate over the northern hemisphere, and so I'm going from 0 not the pi, but the pi over 2, this means I'm restricting to the northern hemisphere. And then my function is 110, and f of phi is just 1 there, so it's 110. It's a constant, and I have to integrate Pn of cos phi d cos phi. And then, of course, I can just make the change of variables to mu if I let mu equals cos phi, and this becomes 110 Pn of mu d mu, and then when phi is equal to pi over 2, mu is equal to 0, and when phi is equal to 0, mu is equal to 1. Okay, so I have a overall negative 110, integrating from 0 up to 1 of Pn of mu d mu. Oh, I'm sorry, I'm missing my normalization factors here. Whenever I have a Sturm-Liouville projection, I need to normalize by the square of the eigenvector. So Pn of cos phi squared d cos phi, and that will still appear here. So 0 to pi Pn squared cos phi d cos phi. Okay, and it turns out that that factor, the normalization factor in the denominator, is 2 over 2n plus 1, so that will come out in front. So this is going to be equal to 2n plus 1 over 2 times 110, and here I need my factor of 2n plus 1 over 2 times 110 times my integral. I have a negative sign because I changed my my limits there. Okay, so now we can look up the formula. There is a formula for the Legendre polynomials, and the formula for the Legendre polynomials looks like this. So Pn of mu, that's going to be a sum from m equals 0 to capital M. I'll define capital M in a moment, -1 to the m, and I have a 2n minus 2m factorial divided by 2 to the n m factorial n minus m factorial n minus 2m factorial. That is a mouthful, and then I still have a mu to the power of n minus 2m. Okay, so this is just, this is nothing more, nothing less than an expression for the Legendre polynomial. It's a polynomial in the variable mu, and we can look that up from chapter 4. We did not have sufficient time to talk about that precise form this semester, but you know, take it for what it is, and we can use it to get an answer here. So I need to integrate this thing from 0 to 1. And so if I integrate from 0 to 1, and the thing that I'm integrating is this object here, I can interchange the limits of summation and integration. And so I'm integrating a power of mu, so this is to the n minus 2m d mu, and so this equals 1 over n minus 2m plus 1. And so since I've interchanged the order of integrating and summing, I can stick in that expression into my series. And so it turns out that my coefficient, a sub n, is going to be 110 over 2. And then notice this 2 to the n I could bring outside. My sum is over the index little m, and this term here is 2 to the n, so I can just bring that out. So I have a 2 to the n in the denominator over here. And what else can I do? I still have my original normalization factors of the 2n plus 1 over 2. Those are sitting over here, so I have my 2n plus 1, and then I had my 2 already. Okay, so that's all that I can pull out of the series, and I still have a sum from m equals 0 to capital M of minus 1 to the m, and this is just the integral of that Legendre polynomial. So I've integrated, remember originally my p sub n was inside the integral. I had a series expression for p sub n itself, and then I'm integrating that series term by term because here's my power of mu. And at the end of the day, I get a 2n minus 2m factorial. And then in the denominator, here I had a factor of n minus 2m factorial. And from the integral, I had an extra factor of n minus 2m plus 1. So at the end of the day, my denominator, after doing the integral, it just shifts the denominator to an m factorial, n minus m factorial, and then this last factorial, because of this extra factor of n minus 2m plus 1, this times that just becomes the factorial of that. So this is n minus 2m plus 1 factorial. So I just absorbed that other factor that came from doing the integration. And this is it. So we have our final expression for the coefficients in the series. And so the only thing that I have to explain a little bit is the terminal capital M. So capital M is equal to n over 2 for n even, n is equal to n minus 1 over 2 for n odd. Okay, so in other words, if we're thinking about the third term in our Fourier-Legendre series, so for n equals 3, then the upper limit would be 1. So I would have two terms in that series. I would have 0 and I would have 1. So little m would be equal to 0 and little m would be equal to 1. That would be the last term. On the other hand, if I was thinking about the fourth term in the series, so a sub 4, then my series would stop at 2. So I have little m equal to 0, little m equal to 1, and little m equal to 2. Okay, so that's how the series terminates. So for instance, if we go through and work this out, so a sub 1 is equal to 110 over 2 over 2 times 1 plus 1 over 2 to the 1. And then I have a sum from m equals 0. And then, so 1 is an odd number, last time I checked. So my upper limit is 0. That means there's really only one term. And so I have minus 1 to the 0. And then I have a 2 times 1 minus 2 times 0 factorial. That's a 2 factorial divided by 0 factorial, also known as 1. And then I have 1 minus 0 factorial. That's also 1. And then finally, I have I'm sorry. I really should have these as m, 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 And so this is 1 minus 2m plus 1 factorial. But the point is that the summation only has a single term in it, the m equals 0 term. So I can stick in 110 over 2. So this is 3 over 2. And then I just have the m equals 0 term in my sum. So this is going to be negative 1 to the 0, which is 1. And then I have 2 minus 0 factorial divided by 0 factorial, 1 minus 0 factorial, and then 1 minus 0 plus 1 factorial. When the smoke clears, that's a 110 divided by 2, 3 halves. Then I have a 2 factorial over a 2 factorial. And that will give me 55 times 3 over 2. And that really can't be reduced anymore. So that's my first coefficient in my series expansion. So if I were to write my function u would be equal to r and again, I'm sorry, so I've been a little sloppy here. So these should all be r to the n. So this is r to the 1. And so my first, so a1 is 1 over r to the 1 times 55 times 3 over 2. So the first term in my expansion for u would be (55) times 3 over 2 times rho to the 1 divided by r to the 1. So notice in each of these terms in my series expansion, I'm going to have rho divided by r to some power. And then I have p sub 1 of cos phi. And it turns out that p sub 1 of mu is just mu itself. So that just becomes cos phi. And I also have my a sub 0 sitting in there somewhere. A sub 0 so for n equals 0, r to the 0, a sub 0 has to be equal to 55. So there are no terms in that expansion there. And so I have a 55 plus 55 times 3 over 2. So this is 55 plus 55 times 3 over 2 rho over r to the 1. And then p1 of mu is just mu, so this is a cos phi. And then I have some other terms that are proportional to rho squared and higher. So we could go through and we could plug in values for n equals 2, n equals 3, and at the end of the day, our entire series would be given by those coefficients multiplied by the appropriate Legendre polynomial. And that's it for now.